Okay, we begin with the chapter stability analysis. Stability analysis is one of the important parameters in the system. So we start with the first thing, bounded input, bounded input, bounded output, abbreviated as BIBO, stability. BIBO stability, bounded input, bounded output stability. We will define what is bounded input, bounded output stability, and then we derive the condition for BIBO stability. Okay, what is BIBO, bounded input, bounded output stability? Any linear relaxed system is said to be BIBO stable if and only if for every bounded input the response remains bounded. What is that? Any linear relaxed system is said to be BIBO stable, BIBO stable if and only if for every bounded input output or a response remains bounded. Remains bounded is the definition of the bounded input, bounded. So bounded means to say it is a finite. When I apply a finite magnitude input with a finite magnitude, the output must be finite. So that is what we mean by bounded input, bounded output stability of the system. And in linear relaxed system means to say that the initial condition is equal to 0. When initial condition is equal to 0, we are checking the stability of that system. Let me go for the condition of BIBO stability of the system. Condition of BIBO stability of the system. Let me consider a closed loop system with the input R of S, the output C of S. So, where we know that R of S is the response in S domain, C of S is the response in the S domain, R of S is the input in the S domain, G of S is the forward path transfer function, H of S is the feedback path transfer function. Overall transfer function is given by overall transfer function of a closed loop system is given by E of S. Let me call that as E of S. E of S is equal to C of S by R of S is equal to G of S 1 plus G of S H of S. Right? 1 plus G of S H of S. Then G of S H of S gives you the open loop transfer function, and of course this ratio gives you overall closed loop transfer function. Among this, 1 plus G of S H of S is termed as characteristic equation. 1 plus G of S H of S is equal to 0 is known as characteristic equation of the system. Characteristic equation of the given system. The 1 plus g, the roots of the characteristic equations, which are nothing but the poles, decides the behavior of the closed loop system, or decides the nature of the closed loop system. Hence, 1 plus g of s h of s is known as characteristic equation. Remember, it is very important. 1 plus g of s h of s is equal to 0 is known as characteristic equation because the roots of characteristic equation decides the behavior or nature of the closed loop system. A1 decides the stability of the, or the roots are nothing but the poles. Okay? Roots of characteristic equation or nothing but poles of T of s, transform overall transfer function T of s. Okay, let me call this as equation 1. We'll continue that. Response in S domain. Response in S domain according to the equation 1, C of S. C of S is equal to, it is T of S into R of S. So let me call this as equation 2. Of course, taking the inverse Laplace transform of equation 2 gives you the response in time domain. So taking inverse Laplace transform of equation 2 we get. So what is that? So C of t gives you the response in time domain. C of t equal to inverse Laplace of C of s. It's equal to inverse Laplace of the product of the Laplace of the overall transfer function T of s, R of s. Okay. So what is this? This inverse Laplace transform of the product of the two functions in S domain can be obtained by convolution integral. Okay. Inverse Laplace transform of T of s and R of s can be obtained by convolution integral. So that is C of t equal to, it is nothing but inverse Laplace transform of C of s is nothing but, this can be given by convolution from limit minus infinity to plus infinity. The response can be written R of t minus tau into e tau d tau. Let me call this as equation 3. So for the bounded input, bounded input mean to say that the R of t minus 2 absolute value of R of t minus tau must be finite. It should be within 0 to infinity, finite, as well as so magnitude always within that value. Bounded input, so that means finite value of input. Okay? Finite value of input. So that is 0 must be less than modulus of R of t minus tau must be less than infinity. Let R of t minus tau be a finite value value say a. I call that designate this magnitude with a finite value say a. Then what the condition is? So absolute value of the response. So absolute value of response is given by the absolute value of the response or magnitude of the response CRT is equal to it is minus infinity to infinity and it is nothing but modulus R of t minus tau. It is modulus of t minus tau t tau. For relaxed system, initial condition is 0. Initial condition is 0. That means response exists from time t equal to 0 to infinity. So when it is a relaxed system, it means that initial condition is 0. Since initial condition is 0, so response can exist from 0 to infinity. So we can change the limit of this convolution integral from 0 to infinity. So what is that? We can then write the equation magnitude of C of modulus of C of t is nothing but from 0 to infinity, whereas this modulus I can replace that by a value a, and I can write here a, it is modulus of t minus tau theta. So for bounded input, it should be finite value. That is what this means. So finite value must be from 0 to infinity. We have taken some constant, and because of that, I got that the output is equal to a 0 to infinity t minus t of tau. So modulus of t of tau t tau. Now what the definition says? It says that for every bounded input, if and only if the output is bounded. What do you mean by the bounded? Oh, if output is finite, then the system is said to be BIBO stability. What is this says? So this should be finite. What is this? So we will come to that one. So for BIBO stability, magnitude of output must be bounded. Means finite. Magnitude of output must be bounded, which means that this thing should be within 0 to infinity. It should not be more than infinity. It should be well within that, or it is finite. So that is which means that so modulus C of t, so a 0 to infinity, modulus of t of tau, t tau must be less than infinity. So if that let the bounded finite value, let magnitude of output be some finite value say m, then that means the magnitude of the C of t, so which is less than infinity, so it is some constant a 0 to infinity t of tau, t tau should be less than m. Okay, that's Now, what is this? We need to see that. What is this? Coming back to the response again, this one. Note that C of S, the response in S domain is the product of the transfer function in S domain and the input. So, if input is impulse, if input is impulse, if input is impulse, that is R of S is equal to delta, R of S is equal to inverse Laplace of delta of t, which is equal to 1. Then the equation 2 simply becomes, so C of S is equal to T of S. T of S. So impulse response so is nothing but L inverse C of S. It is equal to, now it can be written with this from 0 to infinity. So 1 into T of S. So impulse response is nothing but T of tau T tau. Impulse response of the system, which means that when I apply impulse input here, impulse response is nothing but it is the inverse Laplace of the transfer function itself given by the integral 0 to infinity T tau, which means that this is nothing but impulse response. So with this we can conclude that, so that is the equation 3. So whatever the integral of 0 to infinity T of tau d tau is nothing but impulse response, and which means that we can define and conclude that BIBO stability means if the impulse response of the system is finite or bounded, then the output will be bounded, and hence can state that the system is BIBO stable. BIBO stable. Okay. So write that equation 3 indicates that the response remains bounded. Response remains bounded if the impulse response of the given system, is having the finite value. Impulse response of the system is having a finite value. Then the system is said to be BIBO stable. BIBO stable. We simply conclude that for any bounded input, the output must be bounded, that means finite. Then only we can say that the system is stable. So always we check the stability of the system, then only we further go and find the response. If it is not stable, then we cannot further go and find the response of the system. So only if it is stable, then only we consider the response. Otherwise, what we need to do, we have some other methods like need to add controllers or compensator to bring that to bring that to the stability, and then we continue to find the response. Okay, we obtain the condition of BIBO stable system. Then there is one more thing, zero input stability. Zero input stability or asymptotic stability. Zero input stability or asymptotic stability. What is this zero input stability? So before the stability, we will see what is this zero input response. Let us see the definition of zero input response. So we say the response of a system has a zero input when the input applied is zero and response is only because of initial condition. When the response is only because of the initial conditions and the input is zero, then such a response or output is termed as zero input response. So take that one first. So a response of a system only because of initial conditions, when input to the system is zero, is known as zero input response. Next we come to this definition, zero input stability. Zero input stability. When the input to the system is zero and the response is only because of initial conditions, then we expect the response to dice out after a short period of time, or we expect the response to decay towards zero, or otherwise as the time t tends to infinity, the response must goes to zero. Then that system is said to be zero input stable. Otherwise, if the response does not decay to zero, then it is said to be unstable. Okay, unstable. Right then, so zero input stability. When the response of a system decays to zero as time approaches infinity, when subjected to zero input, and only initial conditions, then such a system is said to be zero input stable. Otherwise the system is said to be unstable. Mathematically, we can express zero input stability. It's a very simple thing. So I already proved that for bounded input C of t, it is 0 to infinity, is t of tau must be less than the finite value. Yeah, finite value. Or it should be within 0 to t. For zero input stability, this response of a system must approach to zero or become zero as t tends to infinity. It can be written for zero input stability of the system stability of the system. So modular limit, take a limit t tends to infinity, C of t, modulus of C of t, so that should equal to 0. As time tends to infinity, modulus, that means modulus is telling you the magnitude of the response must approach 0. Then we say third system is stable. Okay? So if not, obviously it is said to be unstable in nature. Now, usually the stability is stated locating the roots of characteristic equation or the poles of the overall closed loop system in the S domain. Okay. So we locate the poles of the closed loop transfer function or roots of characteristic equation, which are nothing but poles, on the S domain to understand the stability of that particular system, whether it is zero input stable or not is depends on the just the location of the poles. So it is very clear that a system will be zero input stable only when all the roots of characteristic equation or poles of closed loop system is in the left half of its plane. Okay, what is this? We will see that. So S is a complex variable, okay, complex frequency usually denoted by this one. Sigma, the real part, the j omega is the imaginary part. So S plane is consists of that. So it's a graph against the real part against the imaginary. So real part is written here, real part, and then imaginary part is over here. So this is your S plane. S plane. What happens now? So this is your left half of S plane. LHS. This is left half of S plane, right half of S plane. Okay. So this is your real axis, imaginary axis. You must aware of all these things. Very important. Left half of S plane, right half of S plane. Then it is the imaginary axis is given here. So here almost this is very common. So yes, we locate. So what is that? So a system is said to be zero input stable when all the roots are there. All the roots are there in the left half of its plane. Okay. Right now the condition is so a system is zero input stable if all the roots of characteristic equation are poles of overall transfer function is in the left half of its plane. Okay, is in the left half of its plane. A system is zero input stable or same thing, so it goes to zero, or it is BIBO stable. Okay, BIBO stable if all the roots of characteristic equation are poles of overall transfer function is in the left half of its plane. Okay, then we say, so for example, let me take one example. T of s is equal to, it is a 10 by s plus 1 into a square plus 2s plus 2 a square plus 2s by 2. So how many poles you have? 3 poles you have. Find the roots of the characteristic equation or denominator polynomial of T of S is called as the roots of denominator polynomial is known as, it is simply the poles. Okay. So let me locate the poles first. So first poles are located at. Poles are located at. So this is equal to 0. S plus 1 is equal to 0. So S is equal to located at minus 1. So tell me what is this? The roots corresponding to this, S is at square plus 2S plus 2 gives you the complex conjugate forms. Minus plus or minus J. Okay. Minus 1 plus or minus 3. Note now. So important thing is that so complex conjugate form is having the negative real part. So if the complex conjugate form, if it has a negative real part, which means that it locates in the left half of plane of the S plane, right? Then we can say the system is stable. We will locate it. So the poles are located by a cross, zeros are located by a small circle. So we can locate it. Suppose this is a pole located at minus 1, then what? I have a 2. Then I have a complex pole. It is located here. 2 poles are located. So J minus J. Note that corresponding to this particular transfer function, the poles are in the left arm of this plane, or it has a negative real part. So if it has a negative real part or in the left half of S plane, then simply we can confidently say that the system is stable. So simply by locating the poles, we can say, or conversely, if any one of the root is there in the right half of S plane, which means that any one roots or poles are there in the right half of S plane, which means that the system is unstable. Any one. Okay? So this is what we mean by zero input stability. So zero input stability is also called as asymptotic stability. Right? So zero input stability is also known as asymptotic stability. Zero input stability is also known as asymptotic stability. So clearly the location of the poles says something related to the stability, right? So left half of S plane clearly says that it is stable. No doubt in that. So let us now work out something. The location of the poles in the S plane and corresponding response. What is the corresponding response? We will see that. Okay. Take the next heading: location of poles in the S plane and their impulse response. So let us now take some example where it locates in the left half of the plane, then on the imaginary and the right half of the plane. What will be the response? Let me start with pole located on real axis in the left half of S. pole, suppose e power minus a located at minus a. So this is the case for if it is a t of t e power minus a. So, yes, in the time domain, if you have this one e power minus a, this is it is impulse response. So we have t equal to t of e power minus a, for which you will get the what is that? C of s is equal to 1 over s plus a. 1 over s plus a. A pole is located exactly at minus a. That is what we have done. Then write that. So we can write this here. C of s is equal to 1 by s plus a. Okay. So we have located that one. So by location of that, I say write that one. So it gives you a suppose here C of t versus time. So it decreases towards it. Second, pole stability stable. Stable. Right? Pole located at origin. Pole located at origin. That means we can see that. So it is the response of impulse response is C of t equal to t of t is equal to, if it is u of t, if this is the nature of the response, then C of x, I write C of x here, it is 1 over s, it is 1 over s. Now I go for s, location of this j omega in s plane, sigma, it is located at the origin. S is equal to 0, pole is at s is equal to 0, located at origin, but it is the response C of t is this. The magnitude is not decaying so obviously according to BIBO or zero input stability. It's in fact it is unstable because constant magnitude. But in control system, we usually discuss, we say this one marginally stable or conditionally stable. Marginally stable or conditionally stable. Marginally stable or conditionally stable. Three, if the pole is located on the real axis in RHS, pole located on real axis in right of S. Right of S. So what happens now? The response in time domain you will get something. So S minus A. S minus A. Now e power at in C of x it is 1 over s minus a in the s plane j omega sigma. It is located somewhere in the right half of x plane. Important to note, right half of s plane. Then the response, impulse response, the right impulse response. So this you will get a response which is the magnitude goes on increasing, and of course that way it is unstable. Unstable. Under stability, you can call it as unstable. Go to fourth one. I have a complex conjugate pair of poles in the left half of X plane. Complex conjugate pair of poles located in left half of a complex conjugate pair of poles located in LX. Remember that this completely describes what do you mean by stability. So entire stability is based on this one, location and their response. Clearly stated. Let me now take any complex conjugate pair located here, somewhere here, J omega. It is S plane. So it is now the nature of the C of t e power minus at say sin omega t. E power minus, so damping, under damping response, the Laplace of this one is equal to, it is S plus A omega S plus A whole square plus omega square. S plus A square plus omega square. So now the nature of this response is obviously, so do this exponential decay with which was like this, goes on decaying that stable. Fifth one. Now the complex conjugate poles located exactly on the imaginary axis. So remember that you already know the step response. So among that you can clearly say that if the poles located to the left of, you get under damped. If it is on imaginary axis, so complex conjugate pair of poles on imaginary axis. What is the complex conjugate poles on the imaginary axis? So which means that it's exactly located on this one. So this is what? So you will get C of t is equal to sin omega t or sin of cosine term, you will get C of s is equal to s square plus omega square. S square plus omega square. If you work out that, you will get that one. The poles are at plus or minus t. Okay, poles are at, or equate this to 0, you will get plus or minus j. Okay, s square plus omega square equal to 0, or s square equal to minus omega square. So s is equal to, it is plus or minus j omega. Okay, so poles are at plus or minus j omega. If this is the situation, what is the response you will get? You will get the undamped response. Undamped response. So that means C of t, undamped response is what you will get. Called as an undamped, so that is this is underdamped response. Okay, somewhere you will write that underdamped response. This is undamped response with the frequency, natural frequency omega n. Undamped response, which, so this is termed as marginally stable. Marginally stable. Then, sixth What is that? If the complex conjugate pairs are there in the right half of S plus, okay? Write that complex conjugate pair, complex conjugate pair of poles in the right half of S plus. Complex conjugate of the. So now what is that? C of t. It is e power at sin omega t. E power at sin omega t. Remember, it is very interesting. So the real part is now positive. So e power at results with the C of x, which is equal to, it is omega s minus a. S minus a whole square plus of omega square. So if you see that the real part, if you equate this to 0 and work out, so what is that you get? S is at a plus or minus j omega. Okay? The two roots with a positive real part. If you work out first, the previous one and attack minus a plus or minus j. That's all. So it is having the negative real part, whereas here it is having positive real part. Okay, complex conjugate. If that is so, what is that? I locate that. Explain. Here I have poles are located in the right half of S. If the poles are there in the right half of S plane, again the obviously response is, it is magnitude is increasing with the time, okay, goes on increasing and it becomes unbounded. This is what we mean, unbounded, becomes unbounded. Goes as the time approaches infinity, that magnitude also approaches infinity. That's what it's called as. This is unbounded nature. So this is unstable. That's known as unstable. Tomorrow. Repeated poles at origin. Repeated roots are roots of characteristic equation are poles of the closed loop transfer function at repeated. Remember, we have seen single root at origin. So note that when it is single root, what happens to the response? When it is single root, go back and see that. And you have a single root, what happens? What is the type of response? Impulse response. 1 by S. It is a step response. We call that as a marginally stable. Need to remember all these things. So if it is repeated poles at origin, this is possible when C of t equal to t. So that means I have a C of s is equal to 1 over s square. Repeated root. So we locate that in the S plane. It is two poles written there. Repeated roots. Two poles are written at origin. When you two poles at origin, remember response is simply linearly increasing as time tends to infinity to t. This is then system is unstable. So in this case it is linearly increasing, repeated roots at origin, gives you a value wherein the response is continuously increasing, and of course when it goes to infinity, the magnitude also goes to infinity. Hence it is unstable. So similarly, last one. Repeated complex pair of poles on imaginary. Repeated complex conjugate poles on the imaginary axis. Repeated complex conjugate poles, and just write the CRS, it is s square plus omega square whole square. All poles are there on the imaginary axis. So again you need to compare that one with a single complex conjugate group or non-repeated poles. Remember, this is very clear. If I have a repeated root, what happens? If I have only one single, note that we have a response here. If we have a one pair of poles on the imaginary axis, it gives you sustained oscillation or undamped oscillation. It's called as a sustained oscillation. Sustained means constant magnitude. Oscillation with constant magnitude or undamped oscillation. It's marginally stable. But if I have a repeated roots on the imaginary axis, then it means that it will give you a response with a complex conjugate group. So damping is being done here. So it continuously increasing, so unstable. It is now unstable. Those are the, with respect to some of the poles located on the S-plane, clearly indicates what happens to the stability of the system. Clearly we can categorize, we have talked about three types of system: stable, marginally stable, unstable. Three types of stability we can say with respect to system based on the location of the poles, right? Location of poles, any number of location of, so can be stable or marginally, conditionally stable. Then we can say it is clearly unstable. What is that, sir? Based on the location of the poles. If all the poles of the closed loop transfer function lies to the left half of S-plane, then clearly it states that the system is stable. If all the poles of the overall transfer function of a closed loop system lies to the left half of S-plane, then it is clearly says that it is stable. Next, if any non-repeated roots or poles, any non-repeated, that means single, if any non-repeated roots lies on the imaginary axis, then we say that the system is marginally stable. The third point is, if any roots or poles of a closed loop transfer function lies to the right of S-plane, clearly it is unstable. Fourth one is, any repeated roots lies on the imaginary axis. Any repeated roots, more than one, at the same place, lies on the imaginary axis. then also it results with the unbounded response, then we call that system is unstable. Okay, 4 points are very clear. Stable when all the poles are lies in the left half of S-plane. One single non-repeated, we call that non-repeated roots lies on the imaginary, marginally stable. If any one of the root of a characteristic equation lies in the right half of S-plane, it is unstable. Further, if repeated roots lies on the imaginary axis, that also leads to unstable. So there are some methods. We will talk about the methods in the next class.